What if I told you that the stage upon which all of existence plays out, the very fabric of space and time itself, might be nothing more than an illusion? What if the cosmos you've known your entire life, with its 3 dimensions of space and 1 dimension of time, is actually just a shadow cast by something far more fundamental, something so alien to our everyday experience that our brains literally cannot visualize it? Right now, at this very moment, leading physicists at institutions like MIT, Princeton, and the Perimeter Institute are making a claim so radical, so fundamentally reality-shattering, that it makes every science fiction movie look conservative by comparison. They're saying that space-time, the thing Einstein proved, was the actual structure of reality, itself doesn't exist at the deepest level of the universe. It's emergent. It's derivative. It's fake. Think about that for a second. The ground beneath your feet, the distance between you and your screen, the past you remember, the future you're moving toward, none of it might be real in the way you think. You're not actually moving through space. Time isn't actually flowing. Everything you've ever experienced might be the universe's most elaborate optical illusion. And here's what makes this absolutely terrifying and exhilarating at the same time. They have evidence. Real, mathematical, experimental evidence. This isn't science fiction anymore. This is the cutting edge of theoretical physics, and it's suggesting that reality as we know it is about to be completely rewritten. By the end of this video, you're going to understand why some of the smartest minds in physics believe we've been wrong about the fundamental nature of reality for over a century. You're going to see how experiments in quantum mechanics, discoveries in black hole physics, and breakthrough mathematical frameworks are all pointing to the same impossible conclusion. And most importantly, you're going to understand what this means for you, for your existence, for the very nature of consciousness itself. But before we dive into this rabbit hole that goes deeper than Alice could have ever imagined, do me a favor, hit that like button right now, because you're about to have your mind completely rewired. Subscribe and turn on notifications, because this is the kind of content that algorithms don't know what to do with, and I need your help to spread this reality-bending knowledge. And drop a comment right now telling me what country you're watching from, and what time it is where you are, because I want to know how far across space and time, or whatever replaces it, this message is traveling. Now, let's start by understanding what we're actually talking about when we say space-time, because you can't appreciate how revolutionary this new thinking is until you understand just how solid, how proven, how absolutely fundamental space-time seemed to be. For most of human history, space and time were treated as completely separate things. Space was this big, empty container that stuff existed in. Think of it like a cosmic stage where the play of existence unfolds. Time was completely different. This invisible river that flowed forward at a constant rate, carrying everything along with it. You had 3 dimensions of space, up and down, left and right, forward and backward, and time was just this separate thing that ticked along independently. This view worked pretty well for everyday life. Newton built his entire physics on it, and those equations got us to the moon. But even Newton had some nagging doubts. What is space made of? Is it actually a thing? Or is it just the relationship between objects? And if space is infinite and empty, why does it seem to have properties? These questions haunted him, but he couldn't answer them with the tools available in the 17th century. Then came 1905, and everything changed. A 26-year-old patent clerk named Albert Einstein, working in his spare time while evaluating patent applications in Bern, Switzerland, published a paper that would forever alter humanity's understanding of reality. The paper was on special relativity, and buried in its mathematics was a revelation so strange that even Einstein's contemporaries struggled to accept it. Space and time aren't separate things. They're woven together into a single, unified entity, space-time. Here's the mind-bending part that you need to really grasp. Einstein showed that when you move through space, you're also moving through time. And the faster you go through space, the slower you go through time. These aren't two separate things that happen to be related. They're literally the same fabric, just experienced from different angles. Think of it like a blanket. You can pull it more in one direction, but when you do, you're pulling it less in another. Space and time are the same blanket, and how much of each you experience depends on how you're moving through the universe. Let me make this concrete with an example that absolutely blew Einstein's mind when he first worked it out. Imagine two twins. One stays on Earth, and the other gets in a spaceship and travels near the speed of light to a distant star and back. When the traveling twin returns, less time has passed for them than for the twin who stayed home. The traveling twin might be 2 years older, while their earthbound sibling aged 50 years. This isn't science fiction. We've measured this with atomic clocks on airplanes. It's real. Time literally slows down when you move fast through space. But Einstein wasn't done. In 1915, he dropped an even bigger bombshell with his theory of general relativity. This is where things get truly surreal. Einstein realized that space-time isn't just some passive stage where physics happens. It's a dynamic, flexible thing that can be bent, warped, and curved. And here's the kicker. Gravity isn't a force pulling objects together. Gravity is the curvature of space-time itself. Picture this. Imagine space-time as a stretched rubber sheet. When you place a bowling ball on it, the sheet curves and dips around the ball. Now, if you roll a marble nearby, it doesn't travel in a straight line. It curves around the depression created by the bowling ball. That's not because the bowling ball is exerting some mysterious force on the marble. It's because the marble is following the straightest possible path through curved space-time. That's what we experience as gravity. The Earth orbits the Sun not because the Sun is pulling on it, but because the Sun's mass curves space-time so severely that Earth's straightest path through that curved space-time is an ellipse. This theory has been tested thousands of times over the past century, and it passes every test with flying colors. We've watched starlight bend around the Sun during eclipses, exactly as Einstein predicted. We've detected gravitational waves, literal ripples in space-time, when black holes collide billions of light years away. GPS satellites have to account for the curvature of space-time, or they'd give you directions that are off by miles. General relativity is one of the most rigorously confirmed theories in all of science. For over 100 years, space-time has been the foundation of physics. It's not just some interesting idea. It's the bedrock upon which we've built our understanding of black holes, the Big Bang, the expansion of the universe, everything. When physicists calculate the orbits of planets, the bending of light, the evolution of the cosmos itself, they're calculating the geometry of space-time. So here's what makes the current moment in physics so absolutely revolutionary. Despite all this evidence, despite a century of confirmation, despite the fact that space-time seems to be the most solid, most fundamental thing in all of physics, there are now multiple lines of evidence suggesting that it's not fundamental at all. That it's emergent, meaning it arises from something deeper, something more basic, something we're only beginning to glimpse. And here's what should really make your mind spin. If space-time isn't fundamental, then what is? What could possibly be more basic than the stage upon which reality itself plays out? What's underneath the foundation of existence? The answer, as we're about to discover, is so weird, so counterintuitive, so alien to everything evolution prepared our brains to understand, that even physicists who work with these ideas every day find them hard to accept emotionally, even though the mathematics forces them to accept them intellectually. Before we go deeper, I need you to understand something crucial. Everything I'm about to tell you isn't speculation or philosophical musing. These ideas are coming from serious physicists, people with Fields Medals and Nobel Prizes, working at the top institutions in the world. They're publishing in peer-reviewed journals. They're proposing experiments. This is real science at the frontier of human knowledge, and it's suggesting that the universe is far stranger than we ever imagined. The cracks in space-time's foundation started appearing not from studying big things like stars and galaxies, but from studying the smallest things possible, the quantum realm. And that's where our journey into the heart of this mystery really begins. Let me set the stage for you. Throughout the 20th century, physicists developed two monumentally successful theories. One was Einstein's general relativity, which describes gravity and the large-scale structure of the universe in terms of curved spacetime. The other was quantum mechanics, which describes the behavior of atoms, electrons, photons, and all the fundamental particles that make up reality. Both theories are spectacularly successful. Both have been confirmed by thousands of experiments. Both make predictions that are accurate to a dozen decimal places or more. There's just one problem. They contradict each other at a fundamental level. They're based on completely incompatible assumptions about how reality works. And when you try to combine them, when you try to make a quantum theory of gravity, or apply general relativity to quantum particles, the mathematics explodes. You get infinities. You get nonsense. You get equations that literally tell you the theory is broken down. This is the single biggest problem in theoretical physics, and it's been haunting the field for nearly a century. It's not just an academic headache. It's telling us that something is deeply wrong with our understanding of nature at the most fundamental level. But here's where it gets interesting. The conflict isn't really about the equations themselves. It's about what those equations assume about spacetime. General relativity assumes spacetime is smooth and continuous, like a perfectly woven fabric that you can zoom into infinitely, and it stays smooth. Quantum mechanics, on the other hand, suggests that if you zoom in far enough to scales about 1 billion times smaller than an atomic nucleus spacetime, should become a seething, chaotic foam of quantum fluctuations, where the very concepts of distance and duration break down. This scale is called the Planck scale, named after physicist Max Planck, and it's at about 1035 meters. To give you a sense of how incredibly tiny that is, a Planck length is to the size of an atom, what an atom is to the size of the solar system. At this scale, quantum effects should make spacetime itself uncertain, fuzzy, probabilistic. The smooth fabric tears apart into something we can barely conceptualize. Now, you might think, okay, so spacetime gets weird at insanely tiny scales. So what? Who cares what happens at scales we can never even observe? But here's the thing: the way spacetime behaves at the smallest scales determines everything else. It determines what kinds of particles can exist, what forces are possible, how black holes work, what happened at the Big Bang. If you don't understand the Planck scale, you don't understand the foundation of reality. And that's exactly where the revolution started. In trying to understand what happens to spacetime at the Planck scale, physicists began to realize something shocking. Maybe the problem isn't that we don't understand spacetime well enough. Maybe the problem is that we're trying to make spacetime fundamental when it actually isn't. One of the first major hints came from black hole physics in the 1970s, discovered by one of the most brilliant physicists of the 20th century, Stephen Hawking. Now, Hawking is famous for a lot of things, but his most revolutionary discovery was that black holes aren't actually completely black. They emit radiation, now called Hawking radiation, and they have a temperature. They're thermodynamic objects. This discovery created what's called the black hole information paradox, and it's this paradox that first suggested spacetime might not be fundamental. Here's the problem. When something falls into a black hole, it seems like the information about that object is lost forever. But quantum mechanics says information can never be destroyed. It's a fundamental principle of physics. So what happens to the information? Does it disappear? Does quantum mechanics break down? Is general relativity wrong? The way physicists eventually started to resolve this paradox is by suggesting something radical. The information that falls into a black hole is actually encoded on the black hole's surface, its event horizon, not in its volume. This is called the holographic principle, and it was developed by Gerard T. Hooft, who won the Nobel Prize in Physics in 1999, and later refined by Leonard Susskind at Stanford University. Think about what this means. All the information about what's inside a three-dimensional region of space can be encoded on its two-dimensional boundary. It's like how a hologram, a two-dimensional piece of plastic, can contain the full three-dimensional image of an object. The universe might work the same way. You, me, everything we see around us in 3 dimensions might actually be information encoded on a distant two-dimensional surface. This is absolutely mind-blowing for multiple reasons. First, it suggests that the 3 dimensions of space we experience might be an illusion, projection from something lower dimensional. Second, it suggests that the actual amount of information in a region of space doesn't scale with its volume, like you'd expect, but with its surface area. And third, it hints that space itself might not be fundamental. If information can be fully encoded on a boundary, maybe what's really fundamental is the information, not the space it seems to occupy. But the holographic principle was just the beginning. The real revolution came from an unexpected direction: string theory. Now, I know string theory has a controversial reputation. It's been criticized for making no testable predictions, for being more mathematics than physics. But whatever else you might think about string theory, it's produced some of the most profound insights into the possible structure of reality we've ever had. String theory proposes that the fundamental constituents of reality aren't point particles, but tiny, vibrating strings of energy. Different vibration patterns of these strings correspond to different particles. An electron is one vibration pattern, a quark is another, a photon is yet another. But here's what's crucial for our discussion. For string theory to be mathematically consistent, the universe needs more than the 3 dimensions of space and 1 dimension of time we're familiar with. It needs 10 or 11 dimensions total. Where are these extra dimensions? The standard answer is that they're curled up, compactified to such tiny sizes that we can't detect them. But here's what changed everything. In the late 1990s, physicist Juan Maldacena, working at Harvard at the time, discovered something called the ADCCFT correspondence. This discovery is so important that many physicists consider it the most significant development in theoretical physics in the past 30 years. Maldacena showed that there's a precise mathematical equivalence between a theory of gravity in a higher dimensional curved spacetime and a quantum theory without gravity in one fewer dimension, living on the boundary of that space. Read that again because it's crucial. You can have 2 completely different theories, one with spacetime and gravity, one without, and they describe exactly the same physics. They're 2 different languages describing the same reality. This is called a duality, and it completely changes how we think about spacetime. If spacetime with gravity in one description is mathematically equivalent to a theory without spacetime or gravity in another description, then spacetime can't be fundamental. It can't be the bedrock of reality because you can describe the same reality without it. Spacetime must be emergent, something that appears from a more fundamental description that doesn't include space or time at all. Let me give you an analogy to make this concrete. Think about temperature. Temperature feels incredibly real, right? You can measure it, you can feel it. Hot and cold seem like fundamental properties of matter. But physics tells us temperature isn't actually fundamental. It's an emergent property arising from the average kinetic energy of molecules moving around. At the level of individual atoms, there's no such thing as temperature. That concept only makes sense when you zoom out and look at vast numbers of particles collectively. What Maldacena's discovery suggests is that spacetime might be like temperature. It's real at the level we experience it. It emerges from the collective behavior of something more fundamental, but at the deepest level, it's not in the basic recipe of reality. Space and time are emergent properties of some more fundamental quantum information. Now, before you think this is all just abstract mathematical games that don't matter for the real world, let me tell you what happened next. Other physicists started finding similar dualities correspondences where spacetime in one description emerges from quantum information in another description. It wasn't just a quirk of one specific theory. It was a pattern. Mark van Ramsdonk at the University of British Columbia made a particularly striking discovery in 2010. He showed that quantum entanglement, this spooky connection Einstein hated where particles remain connected regardless of distance, might actually be what creates spacetime itself. His work suggested that the geometry of space, the very structure of distance and connection in the universe, emerges from the pattern of quantum entanglement between fundamental degrees of freedom. Think about what this means. When we say 2 points in space are close together, what we might really be saying is that the quantum information at those 2 locations is highly entangled. Space is emergent from patterns of quantum entanglement. Distance isn't fundamental quantum correlation, it's fundamental. And distance is just the emergent pattern of how much things are correlated. This idea has been developed further by physicists like Netta Engelhart, Jennifer Lin, Sean Carroll, and dozens of others. They're showing that you can derive the structure of spacetime, including Einstein's equations of general relativity, from the patterns of quantum entanglement in more fundamental theories. Spacetime isn't the starting point, it's the conclusion, the emergent result of something deeper. Let me hit you with another mind-bending implication. If spacetime is emergent from quantum entanglement, then the Big Bang, the supposed beginning of space and time, wasn't really the beginning of everything. It was just the beginning of spacetime as an emergent description. Something more fundamental existed before the Big Bang, even though before doesn't make sense because time itself is emergent. The true fundamental reality is timeless and spaceless, and the universe with space and time that we experience is a particular pattern that emerged from this more fundamental substrate. Are you starting to feel that sense of cognitive dissonance I promised? Good. That means you're really grappling with these ideas. This is the feeling you get when your model of reality is being upgraded, when your brain is being forced to let go of assumptions so deep you didn't even know they were assumptions. And we're just getting started. Because there's another completely independent line of evidence suggesting spacetime isn't fundamental, and it comes from one of the most successful and well-tested theories in all of science, quantum mechanics itself. Let's talk about quantum mechanics for a moment. Because if you think spacetime being emergent is weird, quantum mechanics is where things get truly psychedelic. Quantum mechanics is the theory that describes the behavior of matter and energy at the smallest scales, and it's been tested more rigorously than perhaps any other scientific theory in history. Every piece of modern technology, computers, smartphones, lasers, solar panels, LED lights, medical imaging devices, exists because we understand quantum mechanics. It works, it's real, and it's absolutely, utterly bizarre. Here's the core weirdness of quantum mechanics that matters for our story. Before you measure a quantum particle, it doesn't have definite properties. It exists in what's called a superposition, a combination of all possible states at once. The particle isn't here or there. It's in a sense both here and there simultaneously. It doesn't have a definite position or momentum until you measure it. And here's the kicker. The act of measurement doesn't just reveal what was already there. It actually creates the definite property. Measurement brings reality into being. Now, this has been argued about, philosophized over, and tested for nearly a century. We have experiments, like the double-slit experiment, that prove beyond any doubt that particles really do exist in superposition. We have Bell's theorem, proven by physicist John Stuart Bell in 1964, which shows that quantum mechanics can't be explained by any theory where particles have definite properties all along that we just don't know. The weirdness is real, not just our ignorance. But here's what's crucial for our discussion. In quantum mechanics, not just particles, but fields exist in superposition. And if spacetime is emergent from quantum fields or quantum information, then spacetime itself must exist in quantum superposition before it's measured or observed or interacted with. Spacetime isn't a definite thing, it's a superposition of all possible geometries at once. This is where things get truly mind-bending. What does it mean for space-time itself to be in superposition? It means that, at a fundamental level, there isn't a single definite geometry of space and time. There's a quantum fog of all possible geometries, all possible ways space could be connected, all possible ways time could flow. The definite space-time we experience, where things have clear positions and events have a clear temporal order, emerges only when quantum information becomes correlated in certain ways, when measurements happen, when the quantum superposition collapses or decoheres into a classical reality. Physicist Carlo Rovelli, one of the founders of loop quantum gravity, an alternative approach to quantum gravity that also suggests space-time is emergent, puts it this way. Time doesn't exist at the fundamental level. It's an approximation that emerges from our coarse-grained description of reality, from our ignorance of the exact microstate of the quantum world. Let that sink in for a moment. Time doesn't exist, not at the fundamental level. Your past, your memories, your sense of moving from moment to moment, all of that is an emergent phenomenon, a macroscopic approximation of something far stranger happening at the quantum level. And space? Space might not exist either, at least not in the way we think. The idea that objects are separated by distance, that there's a here and a there, might be just an emergent pattern in how quantum information is organized. At the deepest level, everything might be interconnected in ways that have nothing to do with spatial separation. There's a concept in quantum mechanics called quantum entanglement that makes this concrete. When two particles are entangled, they remain correlated no matter how far apart they are in space. Measure one particle's spin, and you instantly know the spin of the other particle, even if it's on the other side of the galaxy. Einstein called this spooky action at a distance, and hated it because it seemed to violate his theory of relativity, which says nothing can travel faster than light. But here's the twist. If space is emergent from entanglement, then entangled particles aren't actually separated by distance at the fundamental level. They seem far apart in our emergent spacetime description, but at the fundamental level, they're directly connected. There's no distance to cross, no speed limit to violate, because distance itself is emergent. What we call spooky action at a distance isn't action across distance at all. It's the fundamental quantum correlations showing through the veil of emergent spacetime. Physicists Leonard Susskind and Juan Maldacena have even proposed that quantum, entanglement, and wormholes, those theoretical tunnels through spacetime, might be the same thing viewed from different perspectives. The E=EPR conjecture, as it's called, suggests that every pair of entangled particles is connected by a tiny wormhole in the fabric of spacetime. But flip this around. Maybe wormholes, and therefore spacetime geometry itself, are really just the geometric representation of quantum entanglement? Now, I know this is getting heavy. Your brain is probably doing backflips right now, trying to make sense of how reality could work if space and time aren't fundamental. So let me give you another analogy that might help. Think about a computer screen. When you're playing a video game or watching a movie, you see objects at different positions on the screen. Some things are at the top, some at the bottom, some on the left, some on the right. There's a clear sense of space in the image. But zoom into the actual screen, and there are just pixels tiny dots that are either on or off, with no inherent sense of being at the top or at the bottom of anything. The space you perceive in the image is emergent from the pattern of which pixels are lit up. The screen itself doesn't have that structure. The structure emerges in the pattern. Now go deeper. Those pixels are controlled by information stored in the computer's memory ones and zeros in the hard drive and RAM. This information doesn't have any spatial structure at all. Bit number 1,000,000 might be right next to bit number 1,000,001 in the memory chip, but they might control pixels on opposite sides of the screen. The apparent space in the image is completely emergent from how the information is processed and displayed. This is roughly analogous to what physicists are suggesting about reality. At the deepest level, there's quantum information qubits, if you want to think of them that way, organized in some structure that has nothing to do with space or time. The patterns in this quantum information, the ways different bits of information are entangled and correlated, give rise to emergent spacetime when you zoom out and look at the collective behavior. You and I are patterns in that quantum information, and the space between us, the time we experience passing, are all emergent features of how that information is organized. But here's what makes this more than just a cute analogy. Physicists are actually finding ways to test this. If space-time is emergent rather than fundamental, it should have certain properties that we can look for. For instance, there should be a maximum density of information that can be stored in a region of space, which is exactly what the holographic principle predicts and what black hole entropy seems to confirm. The way quantum entanglement between regions of space relates to the geometry of spacetime should follow specific patterns, which is what people working on the E=EPR conjecture are exploring. Some physicists are even proposing that the breakdown of spacetime at the Planck scale, which causes all those infinities and mathematical problems I mentioned earlier, might just be a sign that we're pushing the emergent description beyond its domain of validity. It's like asking what temperature an individual atom has. The question doesn't make sense, because temperature is only defined for large collections of particles. Similarly, asking what the geometry of spacetime is at the Planck scale might be asking a question that doesn't make sense, because spacetime is only defined as an emergent description of large collections of quantum degrees of freedom. Now, before we go further, I need you to do something. Pause for a moment and really reflect on what we've covered so far. We've established that spacetime, the thing you thought was the most fundamental structure of reality, is likely emergent. We've seen how this idea comes from multiple independent directions: black hole physics, string theory dualities, quantum entanglement, the incompatibility of quantum mechanics, and general relativity. This isn't fringe speculation. This is coming from the mainstream of theoretical physics. And here's what should blow your mind. If all this is true, then every assumption you've ever made about reality needs to be re-examined. The past doesn't exist in the way you think. The future isn't a place you're traveling toward. The distance between you and the people you love isn't fundamentally real. Your position in space, your movement through time, your entire lived experience is an emergent pattern in something far stranger and more fundamental. But we're only halfway through this journey. Because now we need to ask, if space-time isn't fundamental, what is? What's the bedrock of reality? What are the truly fundamental ingredients from which everything else emerges? This is where we enter the true frontier of physics, where even the experts aren't sure yet, where multiple competing ideas are being developed and tested. And this is where things get even weirder, if you can believe that's possible. Let me introduce you to some of the leading candidates for what's really fundamental. And fair warning, each one is going to challenge your intuitions in ways that might make emergent spacetime seem almost normal by comparison. The first candidate, and probably the most developed, comes from string theory and its extensions into M theory and a DSCFT correspondence. The proposal here is that what's fundamental are quantum states in what's called a conformal field theory. Essentially, a quantum theory of fields that has no inherent sense of distance or scale, living on the boundary of the spacetime we experience. In this picture, pioneered by Juan Maldacena and extended by thousands of physicists since, the fundamental reality is a holographic screen, a boundary with one fewer dimension than the spacetime we experience. This boundary has quantum fields on it that interact in very specific ways, following the rules of quantum mechanics, but without any of the geometry or gravity of spacetime. When you solve the equations of these quantum fields, out pops spacetime with gravity as an emergent description. Think of it like this. The fundamental reality is a flat surface quantum data on it, like pixels on a screen. But these aren't pixels that make up an image. They're quantum states that encode information. The rules for how these quantum states evolve and interact are such that, when you zoom out and look at the collective behavior, it looks exactly like objects moving through curved spacetime under the influence of gravity. Spacetime is the hologram projected from this quantum boundary. What's remarkable about this is how precise it is. Maldaceno's ADS-CFT correspondence isn't just a vague metaphor, it's an exact mathematical equivalence. You can calculate things on one side using the quantum field theory with no spacetime, and calculate the same things on the other side using general relativity with spacetime and gravity, and you get the exact same answer. They're two languages describing identical physics. This has profound implications. It means that everything that happens in our universe, every star, every galaxy, every particle collision, every thought you've ever had, can, in principle, be described by quantum fields with no spacetime, living on some distant boundary. You are information encoded holographically. Your experience of space and time is your interpretation of patterns in that quantum information. But the ADS-CFT correspondence has a limitation. It works best for universes that are negatively curved, shaped like a saddle rather than like the expanding universe we actually live in. Our universe appears to have a slight positive curvature, or is approximately flat and expanding. So while ADS-CFT gives us incredible insights into how space-time can be emergent, it might not be the final answer for our actual universe. That's where other approaches come in. One of the most exciting is the idea that space-time emerges from something called quantum entanglement structure, pioneered by Mark van Ramsdonk and developed by many others. The basic idea is beautifully simple. The amount of quantum entanglement between different regions of space determines the geometry of spacetime. Here's how it works. Imagine you have a bunch of quantum degrees of freedom. Think of them as qubits if that helps, but don't take that too literally. These qubits are entangled with each other in various ways. Some pairs are highly entangled, others barely entangled at all. What van Ramsdonk showed is that the pattern of entanglement determines a geometry. Qubits that are highly entangled correspond to points in emergent spacetime that are close together. Qubits with little entanglement correspond to points that are far apart. The geometry of space literally, how far apart things are, emerges from how much quantum information different parts of the fundamental substrate share. This is called the entanglement builds geometry, or A equals EPR program, and it's one of the hottest areas in quantum gravity research right now. What makes this so powerful is that it naturally explains some otherwise baffling features of spacetime. For instance, in general relativity, if you have a region of space and you trace over everything outside that region, basically, if you ignore what's going on outside, the boundary of that region has an entropy associated with it. This is the famous Bekenstein-Hawking entropy of black holes, but it applies more generally. Why should ignoring information outside a region create entropy? Because entropy measures entanglement. The entropy on the boundary is measuring how entangled the quantum states inside are with the quantum states outside. Space-time geometry is literally built from these entanglement connections. This approach is also starting to shed light on how time emerges. Time, in this picture, isn't fundamental at all. What's fundamental is the quantum state and its evolution according to quantum mechanics. But different observers, based on what information they have access to, will slice up that quantum evolution into different notions of space and time. Your perception of time, your sense of past, present, and future is a consequence of which quantum information is available to you and how that information is organized. Physicist Don Page, who worked with Stephen Hawking, has developed a concept called the thermal time hypothesis that makes this more precise. The idea is that time is related to entropy, and thermodynamic systems evolve in the direction of increasing entropy, and that defines the arrow of time. But entropy isn't fundamental. Either it's a measure of our ignorance about the quantum state. So time is doubly emergent. It emerges from entropy, which itself emerges from partial information about quantum states. Are you feeling it yet? That sense of everything you thought you knew dissolving into something stranger? Good, because there's another approach to quantum gravity that takes this even further. Loop quantum gravity. Loop quantum gravity, developed primarily by Carlo Rovelli, Lee Smolin, and Abhay Ashtekar, takes a different route than string theory. Instead of adding extra dimensions or holographic boundaries, it tries to quantize spacetime directly. And what it finds is that spacetime, at the Planck scale, isn't continuous at all. It's made of discrete chunks atoms of space, if you will. In loop quantum gravity, space is fundamentally a network. Think of a graph with nodes and links. Each node represents a discrete quantum of volume, about a cubic Planck length in size. Each link represents a discrete quantum of area, connecting adjacent volumes. Spacetime at the fundamental level looks nothing like the smooth fabric Einstein described. It's a seething network of quantum connections, constantly fluctuating and reorganizing. The geometry we experience smooth, continuous space emerges when you zoom out and look at vast numbers of these quantum nodes collectively. It's like pixels on a screen again. Zoom in and you see discrete dots. Zoom out and you see smooth images. Our smooth spacetime is an approximation, valid at large scales, of this fundamentally discrete quantum network. What I love about loop quantum gravity is how it handles the Big Bang. In standard general relativity, if you trace the expansion of the universe backward in time, you hit a singularity, a point where density and curvature become infinite and the equations break down. It's a place where physics simply fails. But in loop quantum gravity, when you approach Planck densities, the quantum nature of geometry kicks in and prevents the singularity. Instead of a Big Bang, you might get a big bounce. The universe could have contracted before our current expansion phase, bounced at the Planck scale, where quantum effects become important, and then expanded. Time might be eternal, with no beginning, and our Big Bang is just one event in an endless cycle. Now these different approaches add CFT holography. Entanglement structure, loop quantum gravity might seem incompatible. They use different mathematics, make different assumptions, and seem to be describing different things. But here's what's fascinating. They're starting to converge. Physicists are finding deep connections between these approaches. The holographic principle appears in all of them. Quantum entanglement plays a crucial role in all of them. The emergence of spacetime from something more fundamental is a common thread. It's as if we're exploring the same mountain from different sides, using different paths, and starting to realize we're all heading toward the same peak. We don't know exactly what we'll find at the top, what the truly fundamental description of reality is, but we can see the outline. It involves quantum information, quantum entanglement, discreteness at the Planck scale, and the emergence of spacetime as a large-scale approximation. And here's something that should absolutely blow your mind. Some physicists are starting to think that the fundamental stuff of reality might not be physical at all. It might be pure information, not information about things, but information as the thing itself. This is the it from bit hypothesis, proposed by physicist John Wheeler late in his career. Wheeler suggested that every physical quantity, every property of particles and fields in spacetime, every it emerges from information, from bits, quantum bits, or qubits. Physical reality is fundamentally information theoretic. Matter and energy in spacetime are all emergent patterns in quantum information. This might sound like mysticism, but it's actually becoming increasingly mainstream in quantum gravity research. If a DSCFT is right, then spacetime with gravity is equivalent to quantum information on a boundary. If entanglement builds geometry, then spacetime structure is information structure. If quantum mechanics is fundamental and spacetime is emergent from quantum states, then what's really fundamental are the quantum states, which are, essentially, information about probabilities and correlations. Some physicists have even proposed that the universe is, in a very precise sense, a quantum computer. Not a computer that calculates anything in particular, just a quantum system evolving according to quantum mechanics and all the apparent structure we see, all the particles and forces and spacetime itself, are emergent patterns in the computational process. Now, I need to emphasize something crucial here. When physicists talk about information being fundamental, they don't mean information in the everyday sense, like the text in a book or the data on a hard drive. They mean something more abstract, the mathematical structure that describes quantum states, the patterns of correlation and entanglement, the answers to yes-no questions about the system. This is quantum information, and it's deeply weird. For one thing, quantum information can't be copied perfectly. That's the no-cloning theorem. Quantum information can be in superposition, existing in multiple states at once. Quantum information can be entangled, where the information about a system is shared between parts in ways that have no classical analog. So when we say reality is information, we're not saying reality is like a computer in your familiar sense. We're saying reality has the abstract mathematical structure of quantum information, which is far stranger than classical information. But let's step back for a moment, because I can feel you starting to get lost in the abstraction. Let me ground this in something concrete. What does it actually mean for you? Right now, watching this video, if space-time is emergent and quantum information is fundamental? First, it means that your experience of being located at a specific place at a specific time is an emergent phenomenon. At the fundamental level, the quantum information that makes up you isn't located anywhere. Location is something that emerges when you consider how that quantum information is entangled and correlated with other quantum information. Second, it means that the flow of time, your sense of moving from past to future, of events happening in sequence, is also emergent. At the fundamental level, there's just a quantum state evolving according to timeless laws. Your perception of time arises from your coarse-grained, partial view of that quantum state, from your inability to access all the information, from the increase in entropy as entanglement spreads. Third, it means that the separation between you and everything else, the distance between you and your loved ones, the space between you and distant stars, is not fundamentally real. At the deepest level, you and everything else are patterns in the same unified quantum state, and the apparent separation is a feature of how that state is organized, how the information is structured. This isn't just philosophical speculation. This is where our best theories of fundamental physics are pointing, and it has profound implications that we're only beginning to explore. For instance, if space-time is emergent, then what we call motion can't be fundamental. You're not actually moving through space as time passes. Instead, the pattern of quantum information that constitutes you is evolving in such a way that, in the emergent space-time description, it looks like motion. You're not moving through space-time. You're a changing pattern in quantum information. And space-time with motion is how that changing pattern looks from the outside. Here's another mind-bender. If time is emergent, then causation, the idea that events in the past cause events in the future, can't be fundamental either. At the quantum level, there's just correlation between different parts of the quantum state. What we call causation is our interpretation of those correlations based on our particular coarse-grained view of the state, our particular way of slicing the quantum evolution into past and future. Some physicists have even suggested that if time is emergent, then the laws of physics as we understand them, laws that describe how things change in time, might also be emergent. The truly fundamental laws might be timeless, describing correlations in the quantum state without any reference to temporal evolution. What we call physical laws might be emerging patterns, regularities that appear when you take a time-like slicing of the fundamental quantum state. This is getting pretty deep into the weeds of quantum gravity research, and I can tell some of you might be feeling overwhelmed. That's okay. That's exactly where you should be at this point. These ideas are at the absolute edge of human understanding. Professional physicists who work on these problems every day find them challenging and counterintuitive. Your brain evolved to help your ancestors survive on the African savanna, not to intuitively grasp the quantum nature of reality. The fact that you're even engaging with these ideas is remarkable. So let's take a step back and ask, why should you care? Why does it matter if space-time is emergent? How does this affect your actual life? These are fair questions, and they're ones that physicists don't always do a good job answering. So let me try to give you some answers that go beyond abstract philosophy. First and most obviously, understanding the fundamental nature of reality is intrinsically valuable. Humans have always asked, what are we? Where do we come from? What is this universe we find ourselves in? For thousands of years, these were purely philosophical or religious questions. But in the past century, they've become scientific questions we can address with mathematics and experiments and observations. And the answer we're discovering is more strange, more profound, more awe-inspiring than almost anyone imagined. That's worth knowing just for its own sake. But beyond that, there are practical implications. Every time we've discovered a new layer of physical reality, it's eventually led to new technologies. When we discovered electromagnetism, we got motors and generators and eventually radio and television and wireless communication. When we discovered quantum mechanics, we got transistors and lasers and computers and smartphones and the entire digital revolution. When we discovered nuclear physics, we got both nuclear power and nuclear weapons. So what happens when we understand quantum gravity? When we truly understand what's fundamental beneath space-time? We don't know yet, but history suggests it will be revolutionary. Some physicists have speculated about quantum computers that exploit the structure of quantum gravity to perform calculations that are impossible with ordinary quantum computers. Others talk about understanding the truly fundamental information content of the universe in ways that might let us probe the deepest questions about why there's something rather than nothing, why the laws of physics have the particular form they do. And there's something else, something perhaps more immediate. Understanding that space-time is emergent might help us understand consciousness. This is speculative. Let me be very clear about that. But hear me out. Consciousness is one of the deepest mysteries in all of science. We don't understand how subjective experience arises from physical processes. We don't understand what makes certain arrangements of matter conscious, while others aren't. We don't understand the relationship between the objective world out there and the subjective experience in here. But here's a provocative thought. If space-time is emergent, if what's fundamental is quantum information and patterns of entanglement, then maybe consciousness is also somehow related to how information is organized and processed. Maybe consciousness emerges from quantum information processing in the brain in a way that's analogous to how space-time emerges from quantum entanglement. I'm not saying consciousness is quantum in some mystical sense. That's usually pseudoscience. But I am saying that we're discovering that reality at its deepest level is not physical objects in space and time. It's information, patterns, relationships. And consciousness is also fundamentally about information, patterns, relationships, about how information is integrated and processed to create a unified experience. Neuroscientist Giulio Tononi has developed a theory called integrated information theory, which proposes that consciousness arises from integrated information that can't be reduced to separate parts. The more integrated the information processing in a system, the more conscious it is. This theory is controversial and far from proven, but here's what's interesting. Integrated information is also closely related to quantum entanglement, which we've seen is what builds space-time geometry. Could there be a connection? Could the same principles that give rise to emergent space-time also give rise to emergent consciousness? Some physicists and philosophers are starting to explore these ideas. I'm not saying they're right. We're nowhere near understanding this yet. But I am saying that understanding space-time is emergent opens up new ways of thinking about consciousness, new possible connections between physics and subjective experience. And that brings me to something personal, something I want you to really feel. If space-time is emergent and quantum information is fundamental, then in a very real sense, you are not separate from the universe. You are not a thing in space-time. You are a pattern in the same quantum information that makes up everything else. The separation between you and the rest of reality is an illusion of the emergent description. At the fundamental level, you and I and everyone else are all aspects of the same unified quantum state. This has echoes of ideas in Eastern philosophy, in Buddhism and Vedanta, about the illusory nature of separation, about the unity of all existence. And it turns out modern physics is arriving at something similar, but from a completely different direction, using mathematics and experiments rather than meditation and introspection. Now, I'm not trying to marry physics and mysticism. They're different enterprises, with different methods and different standards of evidence. But I am saying that physics is discovering that our everyday intuitions about separation and identity and location in space and time are not fundamental truths about reality. They're useful approximations, valid at human scales, but not true at the deepest level. And if that's the case, then maybe we should hold our sense of identity a little more lightly. Maybe we should feel a little less separate, a little more connected to the cosmos. Maybe the existential loneliness that comes from feeling like an isolated speck in a vast, uncaring universe is based on a misunderstanding. You're not a speck in the universe. You're a pattern in the fundamental quantum information that is the universe. This is what I meant at the beginning when I said this journey would change your worldview. I hope you're feeling it now, that sense of wonder, that cognitive dissonance, that simultaneous humility and awe that comes from glimpsing the true strangeness of existence. But we're not done yet, because there's one more layer to this that we need to explore, one more set of implications that's even more profound. If space-time is emergent, we need to ask, what determines which space-time emerges? Why does the quantum information organize itself into this particular geometry, this particular universe, and not some other one? This brings us to one of the deepest questions in all of physics. Why are the laws of physics what they are? Why do we live in a universe with 3 dimensions of space and 1 of time? Why do we have the particular particles and forces we have? Why are the fundamental constants things like the speed of light, the strength of gravity, the mass of the electron set to the values they have? For a long time, physicists hoped there would be a theory of everything that would uniquely determine all these features. String theory, for instance, was hoped to be such a theory. But it turned out string theory has a vast landscape of possible solutions. Perhaps, why I've different possible universes, each with different laws of physics, different particles, different constants. At first, physicists saw this as a problem. If string theory predicts everything, it predicts nothing. It doesn't explain why our particular universe exists. But some physicists turned this into a feature rather than a bug. Maybe all these possible universes exist, they said. Maybe there's a vast multiverse with different regions having different laws of physics, and we happen to find ourselves in one where the laws are right for life to exist. This is the controversial idea of the multiverse, and it's been hotly debated for decades. But here's where it connects to our discussion of emergent spacetime. If spacetime is emergent from quantum information, then maybe different patterns of quantum information give rise to different spacetimes with different physics. The multiverse might not be multiple separate universes. It might be different emergent descriptions of the same underlying quantum reality. Think about it this way. Remember the holographic principle, where a 3-dimensional universe with gravity is equivalent to a 2-dimensional quantum theory without gravity. That's one quantum system giving rise to 2 completely different-looking descriptions. Now, imagine extending this idea. Maybe the fundamental quantum reality, whatever it is, can be described by many different emergent spacetimes, many different effective laws of physics, depending on how you coarse-grain and organize the quantum information. The multiverse might not be out there. Somewhere, it might be different ways of looking at the same fundamental quantum state. You and I experience one particular emergent spacetime, But the same fundamental reality could be described as a different spacetime with different laws by someone or something that organizes the quantum information differently. This is highly speculative, but it's the kind of speculation that serious physicists are engaging in. If spacetime is emergent, then the question why this spacetime might not have a unique answer. Different observers, different ways of accessing the quantum information, might see different emergent spacetimes. The universe might be, in a sense, all possible universes at once at the fundamental level, and we're experiencing one particular slice of that infinite possibility. And here's where this gets really wild. If this is true, then the anthropic principle, the idea that we observe the universe we do because we exist and wouldn't exist in a universe with different laws, takes on new meaning. It's not that we won the cosmic lottery by happening to be in the one universe out of many that supports life. It's that conscious observers like us can only emerge from patterns of quantum information that, when viewed as emergent spacetime, have laws friendly to life. Observers and the observable universe might be two sides of the same coin, both emerging together from the fundamental quantum state. Let me make this more concrete. When you observe something, you're establishing a correlation between your internal quantum state and the quantum state of what you're observing. This entanglement creates a shared structure. Now, if geometry emerges from entanglement, then the act of observation might literally be creating the geometric relationship between you and the observed object. You're not observing a pre-existing spacetime. You're participating in bringing that spacetime into existence through the act of observation. This is not the same as saying you create reality with your thoughts or any such pseudoscientific nonsense. It's much more subtle. It's saying that the division between observer and observed, between subject and object, between in here and out there, is itself part of the emergent spacetime description, not part of the fundamental quantum reality. At the deepest level, observer and observed are just different aspects of the same quantum information, and the apparent separation between them emerges from how that information is organized. Physicist John Wheeler proposed a concept called the participatory universe, the idea that observers are not passive witnesses to reality, but active participants in bringing it into being. At the time, this seemed like philosophical speculation. But if space-time is emergent from quantum information, an observation creates entanglement that builds geometry, and Wheeler's participatory universe might be literally true. Now, before this sounds too mystical, let me emphasize again. This isn't saying you can change reality by thinking about it, or that the universe only exists because we're looking at it. The quantum information is still governed by fixed laws. Quantum mechanics doesn't care about human consciousness. But what is true is that the classical world of definite positions and times, of separated objects moving through space, is not fundamental. It emerges from the quantum world through decoherence and entanglement, and which particular classical world emerges depends on which quantum information gets correlated with which. You are not separate from this process. You are this process. Your brain is a quantum system that's constantly getting entangled with its environment, and in doing so, it's participating in the emergence of the classical spacetime you experience. You're not observing the universe from the outside. You're a pattern of quantum information that's giving rise to an emergent spacetime. And that spacetime includes what you perceive as yourself, as a localized object within it. Do you feel that? That sense of being both insignificant and cosmically significant at the same time. You're a tiny, temporary pattern in the quantum information of the universe. On the emergent spacetime level, you're a fleeting arrangement of particles that will disperse. But you're also a participant in the process by which reality itself emerges. You're not in the universe, you are the universe, experiencing itself from a particular point of view. I promised you at the beginning that this journey would be mind-bending, that it would challenge everything you thought you knew about reality. I hope you're feeling that now. I hope you're feeling that delicious cognitive dissonance, that sense of your model of reality being stretched and reshaped. But I also hope you're feeling something else: awe, wonder, the sheer, staggering beauty of existence. We live in a universe so much stranger, so much more profound than our ancestors could have dreamed. We live in a universe where space and time, the most basic features of our experience, are not fundamental but emergent, where the separation between things is an illusion of perspective, where the flow of time is a consequence of entropy and information, where quantum information, patterns of correlation and entanglement, might be the true fabric of reality. And we live in an age where we can actually figure this out, where we have the mathematics, the experiments, the theoretical frameworks to probe these questions. 100 years ago, we didn't even know quantum mechanics existed. 50 years ago, we hadn't discovered the holographic principle. 20 years ago, we hadn't worked out the connections between entanglement and geometry. Right now, in our lifetime, we're figuring out the fundamental nature of existence. You are living through a revolution in human understanding, as significant as the Copernican revolution, as the discovery of evolution, as the development of quantum mechanics. Future generations will look back at this era the way we look back at the age of Galileo or Darwin or Einstein, as a time when humanity took a giant leap in understanding what and where and why we are. And you have the incredible fortune to be alive for it, to witness it, to understand it. Not everyone will appreciate this. Most people will go through life never wondering about these deep questions, never pushing past the surface appearance of reality to glimpse what lies beneath. But you're here, now, engaging with these ideas, letting them challenge and transform your understanding. So what do you do with this knowledge? How do you live in a universe where space-time is emergent, where separation is illusory, where you are a pattern of quantum information participating in the emergence of reality? I don't have a prescription for you. Everyone will find their own answer. But I can tell you what it means to me, and maybe it will resonate with you too. It means holding your identity more lightly. You are not a fixed thing located at a point in space, persisting through time. You are a pattern, constantly changing, constantly exchanging matter and energy and information with your environment. The you of today is not the same as the you of 10 years ago, except in the continuity of the pattern. And even that continuity is partly an illusion, a story your brain tells to make sense of the flow of information. It means feeling connected to everything. If the fundamental reality is quantum information, and space-time with its separation emerges from that, then you and I and everyone else are all patterns in the same underlying field. We're not separate beings moving through space. We're interconnected aspects of one unified quantum state. The atoms in your body were forged in stars, scattered through space, and assembled into you. You're made of the same stuff as everything else, and at the fundamental level, you're part of the same quantum information structure. It means approaching life with more wonder and less certainty. Every time we think we've figured out reality, we discover a deeper layer. First, we thought the Earth was the center of everything. Then we realized it's a planet orbiting a star. Then we realized our star is one of hundreds of billions in a galaxy, and our galaxy is one of hundreds of billions in the observable universe. Then we realized space-time itself might be curved and dynamic. Now we're realizing space-time might not even be fundamental. What will we discover next? What layers of reality are we still missing? And it means being humbler about the limits of human knowledge, while also being awed by how much we figured out. We're a pattern of quantum information, evolved to survive on one small planet, trying to understand the fundamental nature of existence. We should be terrible at this. Our brains evolved to track predators and find food, not to comprehend quantum gravity. Yet here we are, actually making progress, actually glimpsing the deep structure of reality. That's miraculous. As we approach the end of this journey together, I want to leave you with one final thought, one final mind-bending implication of emergent space-time. If space-time is emergent, then the past and future aren't real in the way we think. There's a fundamental quantum state, and how we slice that state into past and future depends on our perspective, on which information we have access to. The past is real in the sense that it's correlations in the quantum state, but it's not a place that exists somewhere. It's a feature of how we organize information. This means that, in a very real sense, the past is still affecting you now, not because there's some causal chain through time, but because the quantum information that constitutes you now is correlated with the quantum information that constituted past events. You carry the past within you, encoded in the pattern of quantum information that you are. And the future? The future is undetermined, not just because of quantum randomness, but because the future is a notion that only makes sense in the emergent space-time description. At the fundamental level, there's just the quantum state evolving according to quantum mechanics, and our notion of future emerges from our incomplete information about that state. What this means is that you're not traveling through time toward a predetermined future. You're part of a quantum state that's evolving in ways that are partly deterministic, the laws of quantum mechanics, and partly random, quantum measurement outcomes. The future you're moving toward doesn't exist yet. It will emerge from the quantum information as it evolves and as more correlations get established. This is simultaneously liberating and terrifying. Liberating because it means the future is genuinely open, genuinely undetermined. Terrifying because it means there's no cosmic plan, no predetermined path. You're making it up as you go, and making it up means participating in the quantum evolution that gives rise to emergent spacetime with a future in it. But here's the beautiful thing. While the future is undetermined, the past is immutable. The correlations in the quantum state that we interpret as the past are fixed. You can't change the past, but you can change how you relate to it, how you interpret it, what meaning you make from it. And in doing so, you're shaping the pattern of quantum information that you are, and therefore shaping the emergent future that will arise from it. You are a pattern in quantum information, giving rise to emergent spacetime, participating in the unfolding of reality. You are simultaneously insignificant, a temporary fluctuation in the quantum state, and cosmically important and necessary participant in the emergence of this particular universe, this particular spacetime, this particular set of experiences. The universe is not something you're in. You are the universe, experiencing itself, creating itself, understanding itself. Every thought you have, every decision you make, every moment of consciousness you experience is the universe doing what universes do, organizing quantum information in patterns complex enough to reflect on their own existence. And now, having gone through this journey together, you understand something that most humans throughout history haven't known. That space and time, the most basic features of your experience, are not fundamental. That reality at its deepest level is quantum information, patterns of entanglement and correlation. That you are not separate from the cosmos, but an integral part of its quantum fabric. This knowledge doesn't come with a manual for how to live. It doesn't answer all your questions, if anything. It raises new ones. But it does give you a new perspective, a new lens through which to view your existence. You are a brief, beautiful pattern in the quantum information of the universe, experiencing the emergence of spacetime from a particular point of view, contributing your unique perspective to the unfolding of reality. So here's my challenge to you. Take this knowledge and let it change how you see yourself and your place in the universe. Let it humble you. You're a temporary pattern in something unimaginably vast and strange. But also let it empower you. You're a participant in the greatest story ever told, the story of how the universe comes to understand itself. Look around you right now. The room you're in, the device you're watching this on, the space between objects, the flow of time from this moment to the next, all of it is emergent. All of it is quantum information organized in patterns. And you, the observer experiencing all this, are not separate from it. You are it, experiencing itself from the inside. This is the cutting edge of physics in 2026. This is where our best theories are leading us. And while there's still so much we don't know, we haven't confirmed which approach to quantum gravity is correct. We haven't worked out all the details of how space-time emerges. We haven't connected this to consciousness or explained why this particular universe exists. We know enough to say, reality is not what it seems. Before I close, let me give you some homework. First, go outside tonight, if you can, and look up at the stars. But as you do, remember, the space between you and those stars, the time it took for their light to reach you, the distance separating you from them, all of that is emergent. At the fundamental level, you and those distant suns are patterns in the same quantum information, no more truly separated than pixels on a screen. Second, think about someone you love. Think about the space between you, whether they're in the next room or across the world. Remember, that separation is emergent. At the quantum level, if you've ever interacted, you're entangled. You share quantum information. The distance between you is real in the emergent spacetime, but at the fundamental level, you're connected in ways that transcend space. Third, reflect on your past and your future. Your memories, your hopes, your sense of moving from yesterday to today to tomorrow. All of that is your interpretation of patterns in quantum information. The past is correlations in the quantum state. The future is yet to be determined evolution of that state. And you, in this eternal present moment, are the pattern experiencing that evolution as time. Finally, and most importantly, share this knowledge. Talk about it. Think about it. Let it percolate through your consciousness. You're one of a relative handful of humans who understand that space-time is emergent, that quantum information is fundamental, that reality is stranger and more wonderful than we ever imagined. That makes you part of a special community, the community of people who've glimpsed behind the curtain of everyday reality and seen the quantum machinery underneath. If this video has blown your mind, if it's changed how you see reality, hit that like button and share it with someone who needs their mind blown too. Subscribe to the channel because we're going to keep exploring these frontiers of knowledge. Keep diving into the deep questions about the nature of existence. And comment below, what's the most mind-bending implication of emergent spacetime for you? How does this change your worldview? What questions do you still have? Remember that information I asked for at the beginning, what country you're in, what time it is. Here's why that matters. You're experiencing this video in your particular corner of emergent spacetime, at your particular moment in the emergent flow of time. But at the fundamental level, we're all patterns in the same quantum information, and this video is correlating your quantum state with mine, establishing entanglement between your information and disinformation. Space and time separate us in the emergent description, but unite us in the fundamental reality. As I bring this to a close, I want to acknowledge, this has been a long journey. We've covered a lot of ground from Einstein's spacetime to quantum mechanics, from black holes to holography, from string theory to loop quantum gravity, from entanglement to emergence, from the participatory universe to the nature of consciousness. We've explored how space and time might be illusions, how quantum information might be fundamental, how you and I are patterns in a deeper reality. And through it all, I hope you felt what I feel when I think about these ideas. A sense of profound wonder, of being part of something larger than ourselves, of participating in humanity's greatest intellectual adventure. We live in an age of miracles, where the fundamental nature of reality is being revealed to us, where we're learning that the universe is stranger and more beautiful than we ever dared imagine. You've made it to the end of this video, which means you're the kind of person who isn't content with surface appearances, who wants to understand what lies beneath. You're the kind of person who can handle having your mind bent, your assumptions challenged, your worldview transformed. That makes you exactly the kind of person who should be watching this channel, who should be engaging with these ideas, who should be part of the conversation about the nature of reality. The physics community is actively researching these questions right now. In labs and universities around the world, physicists are developing new theories, running new experiments, making new calculations. In the next decade or two, we might finally understand how to reconcile quantum mechanics and gravity. We might confirm that space-time is emergent. We might discover what's truly fundamental. And when that happens, when we have the complete picture, it will be one of the greatest moments in human history. It will be comparable to when Copernicus showed us the Earth orbits the Sun, when Darwin showed us we evolved from other species, when Einstein showed us space-time is curved. It will fundamentally change how we see ourselves and our place in the cosmos. And you'll be ready for it. Because you've already taken the first step. You've already let go of the assumption that space-time is fundamental. You've already opened your mind to the possibility that reality is quantum information, that emergence is everywhere, that the universe is participatory. So thank you for joining me on this journey. Thank you for sticking with me through all the twists and turns, all the mind-bending implications, all the challenges to intuition. Thank you for being curious, for being willing to have your model of reality upgraded, for being part of this cosmic adventure. Remember, you are quantum information, organized in patterns, giving rise to emergent spacetime, experiencing the universe from the inside. You are not in the universe, you are the universe. Knowing itself, understanding itself, marveling at itself. And that is the most mind-blowing thing of all. I'll see you in the next video, where we'll explore more frontiers of knowledge, more deep questions about the nature of existence. Until then, keep wondering, keep questioning, and keep reminding yourself, space-time is not fundamental, and neither is your separation from the cosmos. You are a thread in the fabric of reality. And reality is quantum information all the way down. From one pattern of quantum information to another. Thank you for watching.